Okay, read again the same idea, based on the same idea. Will not be bound. What should be the minimum kinetic in that one? Again, the shall we proceed like this? What all the kinetic energy will supply? So first, what is the diagram? Two identical particles A and B. They are like this. Huh? These are A and B. Then we have like this. Then another particle is kept here and it is projected with a speed v0. This is a particle C. Rigidly attached at the end of light rod. Okay, fine. Now, and the other two are similar to this. For what range of velocity v0 will the particles be bound under their will the particles be bound under their mutual gravitational forces? Will not be bound. For what range of velocity v0 will the particles be bound under their mutual gravitational force? Okay, that one. And if the velocity is greater than that, they don't get bound. If the speed of the projected particle is less than that, they'll get bound. Okay, we'll just do equate things. Then greater than, less than, from that we can make it. No, again, what is the basic idea here? So what all we supply energy, a part of that for kinetic energy of center of mass of system, remaining should be go for the binding energy. What is the binding energy of system? With what energy the particle will get binded to the system? So this is L, no, is given. So 2G. Okay, for first kinetic energy of center of mass. How to bring kinetic energy of center of mass? Kinetic energy of center of mass should be equal to m v naught by 3m v naught by 3. So kinetic energy of center of mass of system off into 3m vcm square plus binding energy. So with what energy it will be binded? 2gm square L. So 3m by 2. What is vcm? v naught by 3 whole square. So this will be 2gm square L. What is the minimum kinetic energy I'm giving? M v naught square by 2. Solving this, we'll get expression 6. I solved it. I ended up this much. 6 gm by L. That L or R naught, what is taken? R naught. Let me change here. No, for what range of velocity v naught will the particles be bound under mutual gravitational force? So what should be the speed? If it is greater than this, they don't get bound. No, if it is less than this, if it is less than this, they'll get bound. So what option shall I pick up? Should not be bound means definitely what happen? It R naught or L. Okay, because R again you'll get confused. Radius something. No, just I made it L, that one. What is the basic necessity condition we should follow here? Should get bound, should not get bound. No, so there's a minimum kinetic energy, minimum speed what we can put. If it is speed greater than this, they'll not get bound. If the speed is less than or equal to, they'll get bound here. So shall we take less than or equal to or less than? Again, one more option C and D is what we have to fight it. So between C and D, what option should be picked up? Shall I take option C? No. Option C or D. See, this is ruled out. Huh? So less than or equal to or less than. What we have to pick up? Less than. No, if it's less than, it get bounded. If it is equal to, what happens? They just, it will not be a bound system. If it's greater than that, definitely what happens? They will escape to infinity. So therefore, it should be the less than. No? There's a minimum speed, that one. If it is a speed greater than this, they don't get bound. Equal to this, again, they just reach infinity. If it is greater than this, even at infinity, they'll have some kinetic energy. So why that minimum I brought it? Are you getting no? If I project with a speed more than this value, after getting separate to infinity, at infinity, they'll have again some kinetic energy. So therefore, I started with the minimum. Escape velocity ideas is what I'm bringing here. In escape velocity, what happened? The Earth was at rest. That's why we didn't bother all this one. So here, what happened? Even this and both will be moving. When you project it, no, this will move. This rod plus this particles A and B will move, and this also will move. See, like, shall I put it simplest way, sir? Why you are discussing all this? If it is the rod AB, if it is a fixed here, tell me what will happen to this one? This will become zero, no? Think about only this one. If since this is also moving, no, then you have to bring this into picture. That's all, finish. I don't want to talk much anything bigger than this one. What we discussed, escape velocity, the idea was like this. What about Earth? Earth was fixed here. Even now we are doing a problem where this Earth is also mobile. If Earth is also mobile, then you should discuss this one. If this is fixed here, then with what kinetic energy you should project? You should project with a kinetic energy equal to binding energy. Getting the idea? You are to analyze. You are not analyzing. That's the problem. In most of the escape velocity problems, we made that particular system. What happened? It was to be a test. Only what happened? The kinetic energy what you project, if it escapes to infinity, or fine. So what kinetic energy equal to binding energy in that case? Here what happened? Even this Earth, if it can move, then kinetic energy of system has to be brought into picture. At least I think now you got certain idea.